good morning. Let's start. Last time we discussed the way we would handle the total angular momentum. So if we had some set of angular momentum, just two actually, two angular momenta. So one of them can be orbital, the other one can be spin. So in general, it could be any two angular momenta. We saw that this J itself obeys the commutation relations associated with angular momentum. So we must have total angular momentum states which are which are which we can use. Okay, so for the original angular momenta states, we have things which look like L1, M1, and then we have an outer product of these things with L2, M2. Okay, so these are the outer product states, but I could also have an Lm which is associated with the total angular momentum. And in particular, we saw last time that we can look at a special case. Okay, the special case was L1, L1, and L2, L2. So this is the angular momentum eigenstates of individual L1 and L2 operators. And those things, okay, those Z components were also set to the maximum values that they can have. And we showed that this is an eigenstate of the J squared and JZ operators. Okay, so over here on this side, I have these things which are eigenstates of L1 squared, L1Z, and L2 squared, L2Z. Okay, whereas over here, this is an eigenstate of J squared and JZ. Okay, so but this object was an eigenstate of J squared and JZ as well. And we found out that that corresponded to L1 plus L2, okay, for the total angular momentum value, and L1 plus L2 for the Z component. Okay, so that is the case when I have both of the angular momenta having their maximum values in the Z direction, and that resulted in a state like this. So obviously I cannot have any state with a higher LZ momentum because this, okay, the LZ component here must be the sum of these two always. Okay, so that means that I cannot have a total angular momentum larger than that also. Okay, so I have this set, and then I can generate the others. Okay, so let me in fact move on to this board. Okay, so and let's work out as an example. Suppose I have an L1 equal to 1 and L2 equal to 1/2 set of states. Okay, so this is going to generate for me M equal to +1, 0, -1. This is going to generate for me, okay, M equal to +1/2 and -1/2. Okay, but the maximum, okay, we saw was going to be 1, 1. Okay, I'm just copying that down. And 1/2, 1/2. So this is the outer product state. And we saw that this is going to be 3/2 state. Okay. Now I can generate further states by looking at, okay, what this is going to generate when I operate on it with a J minus. So if I hit on this with a J minus on the left, 1, 1, 1, 2, okay, 1/2 is equal to J minus 3 over 2, 3 over 2. But now J minus is something very simple, right? J minus is just J1 minus plus J2 minus.
Is it an L1 minus L?
Yes, L, okay, sorry. Thank you. L1 minus plus L2 minus. Okay, so what happens when that operates on that? Now I know that L1 minus will operate only on the first object, okay? And L2 minus is going to operate on the second object. So I'm going to get, okay, a lowering operation on 1, 1. So the first term is going to give me 1, 0, 1/2, 1/2, but there will be a prefactor, right? And the prefactor will be what? Okay, so maybe I'll put it over here. So L minus operating on Lm is going to be square root of L plus 1, okay, minus
M plus 1.
M minus 1, okay? This becomes a minus, and this is L as minus, okay? So I'm going to get here a square root of, okay, 1 times 2 minus 1 times 0. Okay, but I have another term, this L2 minus operating on the second one. So that's going to be plus, okay, 1, 1, 1/2 minus 1/2. And what do I get in the square root? So I have 1/2, one more, 3/2, minus 1/2 minus 1/2. Okay, sorry for squeezing the numbers here, but that's what I have. Okay, so that's that. What about on the right-hand side? Now I can operate with the full J on this thing. So this is going to be square root of 3 over 2 plus, okay, no times 3 over 2 plus 1, which is 5 over 2, minus, okay, M, okay, 3 over 2, and 1, this is 1 over 2, okay? And what do I have? 3 over 2, 1 over 2. Okay, so now I have related one lower set of things. If you remember what we did for the spin case, 1/2 case, it was actually really the same thing. Okay, we started with the 1, 1 state and then went down generating all the triplet states, for example. Okay, so what is this object here? This is 1 over square root of 2. No, this is just square root of 2. This is 3 minus, okay, 3, it's just 1, right?
No, square root of 2.
Both of them are 1.
Yeah, 1, I'm sorry.
Okay, yeah, 3 over 4 minus 1 over, or plus 1 over 4, right? So it just makes 1. Okay, so this is equal to 1. What about over here? I have 15 minus 3 over 4, so it's 12 over 4, which is 3, right? So let me just rewrite this. This says, let me divide by square root of 3. So this says square root of 2 over 3, 1, 0, 1/2, 1/2. okay, plus 1 over square root of 3, 1, 1, 1 half minus a half is equal to, so you see we are generating now all these nice relations. So I divided by square root of 3, so this is just 3 over 2, 1 over 2. Okay? So we found a relation which goes like that. Okay? So I could apply j minus one more time. Okay, then I'm going to get an expression for 3 halves minus a half. Okay? One more time, then I get 3 over 2 minus 3 over 2. Okay? But as you can see, these things can get quite involved, and we don't want to do this algebra all the time. So there's this very nice set of relations. Let me just distribute these things to you. This is just a copy of a page from your textbook. So if you just pass some to the back also. Okay. So these are what's a table which is known as the Clebsch Gordan coefficients. Okay, so I gave everything to you and I don't have one. Okay, so these coefficients that you have here are called the Clebsch Gordan coefficients. And they have been set into tables. So if I can show you a part of this, you'll learn how to use these things. Okay, so you have a whole set of tables there and a number of examples next to them. And once this projector comes out, okay, so this is just a portion of the tables that you have. Okay, so if you look toward the top left of the tables that I just distributed to you, you'll see a piece which says 1 cross 1 half. Okay, so these things correspond to, okay, nice thing about projecting on the board is I can write, this is L1, and this here is L2. Okay, so this is the set of coefficients associated with L1, L2, and their total angular momentum states. So things like these, okay, so if I just go across here, lines that go horizontally, you see this is made up of boxes, L-shaped boxes. Okay, so there's one box here. If you look at the thicker lines, there's another box here, and so on, okay? So each one of these boxes correspond to certain sets of M1 and M2. Okay, so from the left, you have these outer product states. From the top, you have the, okay, actually the L, M states. Okay, so these are the L and M states. Okay, so if you look at, for example, this set of numbers, so I'll just go down here. So what these numbers tell me is that, okay, let's see. I am going to get a, okay, so if I look at the 3 over 2, 1 over 2 state, that's equal to, let me just make sure I'm doing the right thing here. Okay, so I have Okay, so I know what the result is, so I can just cheat and look over there. I'm going to get square root of 2 over 3 for this one, okay? And 1 over 3 for that one. Now, you see, in this table, everything should really go under a square root, okay? So in order to make the table simple, we don't write the square roots, but a square root is implied. Okay, so there's a square root associated with everything here. If there's a minus sign, the minus sign goes outside the square root. Okay, so that you don't have any imaginary numbers. Okay, so that quantity, 3 over 2, 1 over 2, is going to be made up of, okay, so let me now look at this. I'm a little confused actually, but that's okay, we'll figure it out. The M1 and M2, okay, let's see. Yeah, okay. So this term here, this is associated with, let me get my eraser and put that over here. So this is associated with 1, 1 and 1/2 minus a half. Okay, so this 1 comes from there. This 1/2 comes from there. This one is that one. That minus a half is that one. Okay, so these are the M values. Okay, and these are the associated coefficients. The first one is 1 over square root of 3. Okay, so I get 1 over square root of 3 times 1, 1. 1/2 minus a half. And then I have 1 plus square root of 2 over 3. Okay, and that corresponds to, okay, this one, 1. Let's see, where am I? 1, 0. And 1/2, 1/2, right? That's what I have over there. Right? Okay, so that's correct. Okay, so we just look at this row and we find out that this is, okay, I'm sorry, let me just reinterpret this. We are doing it correctly, but I just wrote a different relation for it. Okay, so this first line is associated with 1, 1/2 minus a half, which is, I think, something which I just erased. And this is associated with 1, 0, 1/2, 1/2. Okay? So I pick out the L value from this part and the M values from that part. So I get this coefficient or that coefficient. Okay, so I relate this thing, which is, okay, so this column here corresponds to 3 over 2, 1 over 2. Okay, so 3 over 2, 1 over 2 is made up of these two pieces, which is 1 over square root of 3 and 2 over square root of 3. Okay? Okay, now we are going to, okay, so if we are now considering these two outer product states, then I have to look at one of these, okay, total angular momentum states. Okay, so let's just look at this one, for example. Okay, so this line is going to tell to me 3 over 2 minus a half is equal to, okay, square root of 2 over 3, 1, 0, 1/2 minus a half, right? So I just wrote this down, and then plus 1 over root 3, 1 minus 1, and 1/2. Okay, so now if you look at the z components of this thing, you see if you add the z components, that's minus a half. If you add the z components here, it's minus a half. And I also have minus a half on the left. So the z components must always add up. Okay, so the z components on the left-hand side and the right-hand side must always be the same. Okay, so here I have plus a half. So let's see. Why do I get myself into trouble? Okay, 3 over 2, 1/2. Where is that? 3 over 2, 1/2. Okay, so what did I do wrong? Yeah, okay, I put down the wrong things here. So 3 over 2, 1/2, I should be using this stuff, right? So this line is out. Okay, so I try to interpret these things as the Clebsch Gordan coefficients. The Clebsch Gordan coefficients are always in these lower right, okay, pieces, over here, over there, and over there. So this one, for example, is trivial. This says 3 over 2 minus 3 over 2 is just equal to this 1 minus 1 and 1/2 minus a half. Okay? So, sorry for the confusion, but okay, so the Clebsch Gordan coefficients are always in these pieces which are to the right. Okay, the ones to the left of those are just the indices for these things. Okay? And so it goes. Okay, I hope I have clarified a little bit. In the handouts that I gave you, okay, I have worked out everything in this case. Now, you see what we have done here is we have expanded these total angular momentum states in terms of the outer product states. But because of the symmetry of these coefficients, I could have also done the opposite. So let me just remove these things and let me try to go this time horizontally on the table instead of vertically. So what I can also do is I can take, for example, this line. Okay, so this time I am looking at 1, 1 and 1/2 minus a half is equal to, you see now I can move across the table towards the right and expand this in terms of the total angular momentum state. So I'm going to get 1 over root 3, okay, 3 over 2, 1/2, okay, plus square root of 2 over 3, 1/2, 1/2, okay. So I can also expand this outer product state in terms of the total angular momentum states working towards the right. Okay, so let's do one more. For example, if I take this 1 minus 1, 1/2, 1/2 is equal to, okay, so I shouldn't be fooled by this part, which it's just an indication of this and not coefficients. Okay, the coefficients are over here, and the coefficients are 1 over root 3 of this thing, 3 over 2 minus a half, okay, plus square root of 1 over 3, okay, 1/2 minus a half. Okay, so they are a set of useful tables, so you don't have to calculate these coefficients, except you have to find a way to use the table, obviously, without making mistakes. In any case, you can move left to right or up and down and generate all of these coefficients. Any questions?
Then I don't understand the second term.
Second term, you mean this one or the whole term?
The second one.
The second one is, okay, provided I didn't, okay, so if you don't understand something, most likely I made a mistake. So it's this one, right? So I am putting in these coefficients, okay, this one and that one. So this is 1 over 3, so this is going to be, you're right, minus 2 over 3, okay, times that.
Hocam, why did you look at the horizontal coefficients? Don't you look in the rows, like columns?
Okay, if you want to expand this in terms of the total angular momentum states, okay?
It works both ways.
Yeah, so that's that. Okay, so please do some exercises and familiarize yourself with the table more than my capabilities, okay. So these things are useful. If you have more complicated systems, as you can see in the tables get somewhat bigger. And obviously, there are also computer code, etc., which generate these numbers if you need to implement them in your calculations. But otherwise, just for one-shot type of things, these are very useful tables.
I have a question.
Sure.
Do the sums of rows and absolute value of elements in rows and columns always add up to 1?
Yes, the squares,
Yeah.
right? Square, because you see, this is really. So let's discuss what this means. Now, if we put a particle, okay, two particles, into the system with these angular momenta, okay? So suppose, let's make a more specific example. Suppose at a certain time, I measure the total angular momentum and z component of a particle in an atom, for example, okay? So in that case, we know that the orbital angular momentum can be measured, and suppose I find L equal to 1 and z equal to minus 1. I measure the spin of the electron, okay, and I find that it's plus a half in the z direction. Now, suppose the system has an interaction, okay, or I can make a independent measurement of the total angular momentum and the total spin, total z component of the angular momentum. What will I measure? Okay, so in the sense of our measurements, so suppose I measure L1 squared, a set of measurements. These are all going to be compatible. So this gives me, okay, 1. Okay, I get a value of h bar. And then I measure L1z, and I get minus h bar. So what does that mean? The particle is in this state. And then I don't have to measure the total angular momentum for the electron spin because I know it has to be 1/2, but I measure the spin of the second particle. So let me say S. Okay, so and I get plus h bar over 2. So at this point, I know definitely that the particle is in 1 minus 1, 1/2, and 1/2 state. You see, these are all compatible measurements. This L1 and L1z are in one Hilbert space. This object is in the other one. So these measurements do not interfere with one another. But now suppose I want to measure the total angular momentum, okay, J squared. What are the possibilities? I'm going to get either 3 over 2, okay, or 1 half. Okay, by the way, I should write this as 2h bar, right? Because I get L plus 1. So this corresponds to L equal to 1. So L plus 1 is equal to 2, right? And h bar squared. Okay. So now, if I want to measure J squared, there are 2 possibilities. I can either get an L equal to 3 over 2 measurement or an L equal to 1 over 2 measurement. Okay, those are the only possibilities. And what are the probabilities? The probability of this one is equal to 1/3. The probability of this one is 2/3. Yes.
Hocam, in a physical sense, how do we measure the angular momentum of these 2 separate particles separately? How do you perform the measurement?
Well, it depends on the problem, right? So how do we measure these 2 quantities separate from one another? One is, okay, an orbital angular momentum, and the other one is a spin. Okay, so it really is the imagination of the experimentalists to measure these things separately. These things have different amounts of magnetic moment associated with them. So one thing might be measuring the magnetic moment and such things. The total angular momentum is usually measured by, okay, you see, why are we emphasizing, let me move over here. Why are we emphasizing this total angular momentum so much? You see, if you have, for example, orbital angular momentum and spin, you have the nucleus here, the electron moving around it with some angular momentum. So it has some angular momentum L. That angular momentum L is going to be associated with a magnetic field that is observed by the electron, because the electron is going around the nucleus. So from the perspective of the electron, the nucleus is going around the electron, right? So it generates something like a current. So it's associated with some magnetic field. Now, if you look at the energy associated with the magnetic dipole moment inside that magnetic field, okay, we know that it's in the form of, okay, magnetic field dot the magnetic moment. So I'm going to get a term which looks like this. So these things, this type of coupling is called a spin-orbit coupling. Okay, this is the spin, and this other one is the orbit. Okay, this is spin-orbit coupling brings in terms of the form L dot S into an Hamiltonian. So now if I look at the total angular momentum, and in fact it's squared, it's going to be L plus S squared. So I'm going to get L squared plus S squared plus 2L dot S. You see, I get the L dot S term here. So L dot S is equal to 1/2 J squared minus L squared minus S squared. Okay. Now, you see, if I have a total angular momentum state, then I know, in fact, it's an eigenfunction of this state, right? So if I have L dot S operating on some L m total angular momentum state, okay, that means this is 1/2 J squared minus L squared minus S squared operating on L m. But now this is an eigenstate of all of these operators, right? So this is going to give me 1/2 h bar squared, because everything will give me an h bar squared. And this is going to give me L plus 1 minus, okay, L1 plus 1. And spin is always 1/2 times 3 over 2, okay, 3 over 4 times Lm. So total angular momentum states are eigenfunctions of terms like L dot S, okay? So the energy levels corresponding to spin orbit coupling will correspond to different total angular momenta. Okay, so it is a measure of this L dot S, which in fact is a measure of the total angular momentum. So measuring total angular momentum is usually easy, and that's what you want to do. Measuring the spin and the orbital angular momentum separately is probably going to be somewhat tricky, but it can be done because these are commuting operators and they are compatible with one another, so it shouldn't be a problem. Okay, yes?
Hocam, I couldn't understand this measurement stuff. We measured L1Z,
Okay.
and how can we know, how can it affect the spin measurement? We said
It's
gonna
not.
definitely come out 1 minus 1.
No, it doesn't affect the spin measurement. Okay, let's go through it again. I measure L1 squared, I measure L1Z, okay, and then I measure the spin of the second object. Okay, so it could be anything. But if I suppose it does come out like this, okay, if it does come out like this, then I know that the particle is in this state. Okay, once it's in that state, then I can just go ahead and make my measurements for the total angular momentum state. Okay. Other questions? Let's see what we are doing on time. Okay, let's do the following, because we are now going to drop this subject. That's all I want to discuss about total angular momentum. And we'll start the radial equation for the three-dimensional problem. So let's have an early break, only 10 minutes again, please, and then we'll start the other one.